continuing our theme of solving geometric measurement problems using integrals, let's think about surface areas. So one way that you can generate a surface area is if you take the graph of a function like this, y equals f of x, and between two x values, so say a and b, and so we're talking about this red portion of the graph, and then spin that portion of the graph around an axis. So for now, let's rotate this around the x-axis. When we do that, we get this sort of, I don't know what to call this shape. It's sort of like some sort of vase shape, I guess. This general sort of shape is called a surface of rotation because we generated it by rotating a graph. So we get this surface of rotation, and it sweeps out some surface area on the sides here. Now, I'm not talking about the right-hand end or the left-hand end. Those are sort of open circles on the sides. I'm just talking about the surface area that the graph itself sweeps out as it's rotated around the x-axis. So we could ask, what is the amount of surface area that gets swept out here? Well, as usual, if we're thinking about some difficult geometric problem, the right way to approach it is to break it down into very tiny pieces, find the surface area of one tiny piece, and then put all of those pieces back together using an integral. So in this situation, x's are independent variables, so let's look at the surface area we get just from a single x value. Okay, so at a single x value, there's a little bit of arc length right here, right? A little chunk of arc length on the graph that sits at this x value. What is the name for that arc length? Well, the name for a little chunk of arc length is ds. Okay, so when this little chunk of arc length gets rotated around the x-axis, it sweeps out this sort of band of area, this very thin band like this. Something like this. It's a little hard to draw because it's so thin. So the radius, right? So the radius that this bit of arc length is moving around is this red distance here. Okay. So to get the area of just this one band, we need to figure out, well, how could we take the arc length of this starting segment and figure out how much area it sweeps out. So for a good first guess on how this should work, we have this very tiny bit of arc length, which has length ds, and so length ds, and it's moving. So how far is it moving? Well, it's moving around a circle with radius, the radius of the circle is moving around is this red distance here, but that red distance is just f of x. Okay, so it seems like the area should be the length of the line segment that's moving, which is ds, times the distance that it moves, and it's moving around a circle with radius f of x. So the circumference of a circle with radius f of x is 2 pi times the radius, which is f of x. Okay. Now this intuition does have one caveat, which is that the direction that this small segment is moving has to be perpendicular to the small line segment. But in this case, it is. As it rotates, this small bit of arc length is always perpendicular to the direction that it's moving in. So this seems a little more likely. It's actually a little bit trickier than that, because if you think carefully about the shape that this small bit of arc length sweeps out, it's actually the base, a band around the base of a cone, right? So we have this very narrow band like this, and you can imagine that if you followed the sides down, they'd make a cone. So this shape isn't really just part of a cylinder, it's part of a cone. And so this area formula actually is a little bit questionable. In fact, this is the correct area formula, and in another video I will go through sort of the nitty-gritty technical justification for why this is correct. But for now, let's just take this for granted. It sort of feels correct, I guess you could say. Our intuition sort of guides us in this way. And in fact, it is correct if you go through the technical details. So we'll go through the technical details later. So this is the area of just one of these single bands. So to add the area of them all together, we'll just integrate. So the total area is the integral from a to b of 2 pi f of x ds. Oh, sorry, not dx, ds. All right. Now, if we're using x as our independent variable, then we should write ds in terms of x. And so it will look like integral from a to b, 2 pi f of x times. Now, from our work with arc length, we know that ds in terms of x is the square root of 1 plus dy dx. Well, y is f of x, so dy dx is f of x. So derivative of that squared dx. Okay, so this is if you're rotating a function of x around the x-axis, this will give you the area that it sweeps out. There are some variations on this. So all of the variations on this surface area idea, all of them look like the integral of 2 pi times some sort of radius times ds. And then depending on what the independent variable is and which axis you're rotating around, r and ds will look a little bit different. So this formula was the variable was x, and the axis of rotation was also the x-axis. Okay, so let's look at the situation when the variable is still x, but the axis of rotation is y. So in that case, we have some function of x, y equals f of x, and we're rotating it this way. Right, so now we have a little bit of arc length, and it goes around like this. Sorry, that's a terrible picture. And now the radius of the circle that it's rotating around is this distance, right? And remember, this is the bit of arc length at x. Okay, so if we use this geometric formula for this independent variable is x and the axis we're rotating around is the y-axis, we're going to integrate 2 pi times the radius. But in this situation, the radius isn't f of x. The radius is this horizontal distance, but that's x. So the radius is just x in this case. And then we need a ds right here. But since the independent variable is x, ds is the square root of 1 plus f of x, sorry, derivative of f of x squared dx. Okay, so this is if the independent variable is y and the axis you're rotating around, sorry, independent variable is x and the axis you're rotating around is y. Let's look at one other variation, which is when the independent variable is y and the axis is also y. So if the independent variable is y, that means that you must have a function of y instead of x. So it would look like x equals f of y. and we're going from, say, y equals a to y equals b, like this, we're rotating around the y-axis. So we get something like this. So a terrible picture, my apologies. Okay, so we're going to integrate from a to b, 2 pi times the radius. And in this situation, right, when we have a speck of arc length here, it rotates around this circle, and the radius of that circle is this red length, and the length of this is f of y, right? Really, the length of this is x, but we're writing everything in terms of y, and so we have to write x in terms of y, and that's what the function does. It writes x in terms of y. So the radius here is f of y, and now we need to write ds, but if our independent variable is y, then ds is the square root of 1 plus, right here is going to be dx dy, but if x is f of y, then dx dy is the derivative of this, which is f prime, so f prime of y squared times dy. So this is if the independent variable is y, and the axis you're rotating around is also the y-axis. So there's one more combination, which is when the independent variable is y and the axis is x, and I'll leave that as an exercise, so you can use everything that you've seen so far to figure out the formula for this one. I don't think it's really worth it to know these individual formulas. I think the thing to know, the idea to keep in mind, is this general purpose formula, because it really tells you what's going on, right? We have a bit of arc length, which is ds. That arc length is moving around a circle whose radius is r, and so the circumference of the circle that it's moving around is 2 pi r. So for me, this formula is much easier to remember because it's connected to the geometry of the situation, and it's also more flexible because you can use it no matter what your independent variable or your axis of rotation is. So I think this is the way to think about it.